There are many cases in which a researcher is interested in estimation of a population proportion. For example, population proportion of all U.S. adults who approve of the president's job performance, or maybe the proportion of all parts manufactured by a factory that are defective. In all of these problems, the researcher is observing qualitative data. That is, it's either yes, no, or success versus failure outcomes, rather than actual quantitative data. Here, for qualitative data, we'll use the sample proportion to estimate the population proportion. And this is just like the case for quantitative data, where we use the sample mean to estimate the population mean. So we'll talk about the sample proportion, p hat, large samples confidence interval for a proportion, accurate confidence intervals for a proportion, choosing a sample size, and significant tests for a proportion. So our discussion of statistical inference to this point is concerned making inferences about population means. Now we'll turn to the questions of proportions of some outcome in the population. So, for example, in a random sample of 1,500 people, 11% believe that President Obama was not born in the U.S. Based on these data, what can we say about the percentage of all Americans? Another example, in a random sample of 2,000 men and women aged 19 to 25, 44% of men and 35% of women live at home. Is there evidence that the proportion of all men and all women in this age group differ significantly? So in the first example, we want to estimate the population proportion. In the second example, we want to compare two population proportions. So, a little terminology. When we talk about the number of successes, we mean the number of outcomes that satisfy the particular criteria we are considering. The number of failures is the number of outcomes that don't satisfy the criteria. So, example, suppose we're interested in the proportion of rainy days that occur in 1 year. Each day it rains is a success. Each day it doesn't rain is called a failure. If 1 year it rains 83 days out of 365, the number of successes is 83, and the number of failures is 282. In general, a population has some fixed proportion of successes related to the variable we're considering. We'll denote that with a p. We take a sample and obtain a proportion of successes in the sample. We call that p hat. So how good is the statistic p hat as an estimate of the parameter p? As we did with sample means, we'll look at the distribution of sample proportions. So we have a dot plot here that shows the distribution of 300 random sample proportions of size 25. The actual population proportion is 0.18. Notice the green arrow sort of indicates that the high point of the distribution is around 0.18 in each case. Okay, so these are just different distributions. So what did you notice about the shape, center, and spread of each sampling distribution? Well, the shape, in some cases, the distribution can be approximated by a normal curve. This seems to depend on both the sample size and the population proportion. The mean of the distribution is equal to the population proportion. This kind of makes sense because the sample proportion is an unbiased estimator of the population proportion. The spread, for a specific value of p, the standard deviation gets smaller as n gets larger, as we saw with sample means. And the value of the standard deviation of this distribution of proportions depends on both n and p. And there's an important connection between the sample proportion and the number of successes in the sample. P hat is just simply the count of successes in the sample divided by the size of the sample. That shouldn't come as a surprise. So we're interested in some of the statistics associated with the sampling distribution of a sample proportion. If we choose a simple random sample of size n from a population size capital N with proportion p of successes, and we'll let p hat be the sample proportion of successes, then the mean of the sampling distribution is p, the population proportion. The standard deviation of the sampling distribution is given by this formula, where we have the population proportion times 1 minus the proportion over n and the square root of that. As n increases, the sampling distribution becomes approximately normal. So again, we're taking random samples of size n, and we calculate their population proportions, and we're looking at the distribution of those proportions. And they fall along the horizontal line with this particular shape in the distribution. The mean of the distribution is the same as the population proportion, and the standard deviation is given by that formula. So, constructing a confidence interval for an unknown population proportion is basically the same as a confidence interval for an unknown population mean. It's the statistic, the sample statistic, plus or minus some critical value, times the standard deviation of the statistic. The sample proportion p hat is the statistic we use to estimate the population proportion p. When the independent condition is met, the standard deviation of the sampling distribution is given by this formula. But, as was the case with sample means, we usually don't know the population proportion. That's what we're trying to find out. So we need to replace it with the sample proportion p hat. This gives us what's called the standard error of the sample proportion. So it's essentially the same. We're just replacing the population value with the sample value. So how do we find the critical value? Well, if the normal condition is met, we can use the normal curve. So to find a level C confidence interval, we need to catch the central area under the standard normal curve, like we've done all before. So for a 95% confidence interval, we use a critical value of 2, or actually 1.96, as the critical value. So here for a 95% confidence level, as we had before, the critical z value is 1.96. Notice in this case we're using the z table and not the t distribution, because these are actually normally distributed. So let's find the critical value for an 80% confidence interval. We'll assume that the normal condition is met. We'll use table C to find the z star value, the critical z value. So we locate the column with 80% confidence level and look down toward the bottom of the table where the row for z star is located. And the corresponding z star value is 1.282. That's our critical value. Once we find the critical value, the confidence interval for the population proportion is given by this formula. P hat plus or minus some margin of error. In this case, that's the critical z value times the square root of p hat times 1 minus p hat divided by the sample size. Now, one of the conditions here, and why we're calling it a large sample confidence interval, we want to use this interval only when the number of successes and failures in the sample are both at least 15. For values less than that, we need to use another procedure we'll talk about. So, here's an example. Your teacher claims that 50% of the beads in a container are red. A random sample of 251 beads is selected, of which 107 are red. we want to calculate and interpret a 90% confidence interval for the proportion of red beads in the container. And we'll use the interval to comment on the claim. So it's the sample proportion, 107 divided by 251 is 0.426. This is a simple random sample. There are 107 successes and 144 failures. Both of these are greater than 15, so we're okay using this procedure. We find the critical value for a 90% confidence interval. That's 1.645. And then we take the formula and plug in our numbers. So p hat in this case is 0.426 plus or minus the critical z-value times the sample proportion times 1 minus the sample proportion over the sample size, and take the square root. So if we crank through those formulas, the margin of error is 0.051, and the confidence interval is 0.375 to 0.477. So we are 90% confident that the interval from 0.375 to 0.477 captures the actual proportion of red beads in the container. Now, this interval gives a range of plausible values, and the teacher claimed that 50% of the beads are red. This interval does not contain 0.5, so we have reason to doubt the claim. The confidence interval given by this formula for a sample proportion is easy to calculate and understand because it's based directly on the approximately normal distribution of the sample proportion. Unfortunately, confidence levels from this interval are often inaccurate unless the sample is very large. The actual confidence level is usually less than the confidence level you asked for in choosing a z-star. So there's a simple modification that actually changes the accuracy of the confidence interval. It's called the +4 method, and all we need to do is add 4 imaginary observations, 2 successes, and 2 failures. So the +4 estimate of p, and we need to give it a slightly different notation, so we'll call it p twiddle with the little tilde on top. It's the number of successes in the sample plus 2 divided by the sample size plus 4. So we choose a simple random sample to get the +4 confidence interval for the population proportion. We add 4 imaginary observations, 2 successes, and 2 failures, and then use the large sample confidence interval with the new sample size and number of successes. So we're just replacing the p hat in this case with p twiddle. And we can use this interval when the confidence level is at least 90% and the sample size n is at least 10, with any counts of successes or failures. That's one advantage. We don't need as large a sample, and we can use it with fewer successes or failures. So let's try this out. A microchip manufacturer wants to determine the proportion of defective chips produced by its machines. A random sample of 400 chips is selected and tested. 8 of these were found to be defective, and we want to construct a 95% confidence interval for the true proportion of defective chips of the manufacturer. So the +4 estimate for the population proportion is p twiddle equals the number of defectives plus 2 divided by the number of the sample size plus 4. So we had 8 defective chips found and 400 chips altogether. So we have 10 divided by 404, or about 0.0248. And the 95% confidence interval, z-star equals 1.96. We calculate the confidence interval using this formula. Again, just plugging in some numbers. And our margin of error is about 0.0152. And we estimate with 95% confidence that the proportion of defective chips for the entire population is between 0.017 and 0.047. Now, when planning a study, we might want to choose a sample size that allows us to estimate a population proportion within some given margin of error. We did this with population means. So we know that the margin of error for a confidence interval for a proportion is z star times the standard error, where z star is the critical value. So because the margin of error involves the sample proportion, we have to actually guess what this value is when choosing a sample size. Since we haven't actually collected the sample, we need to estimate, just to guess. And there are two ways to do this. We can use our best guess based on past experience or a pilot study, or we can just use p hat equals 0.5 as the guess. The margin of error is the largest when p hat equals 0.5, so this is a conservative estimate. So we'd basically just solve the formula above for n. And in this case, we are introducing yet another notation. So p star in this case is just the guessed value for the sample proportion. The margin of error will always be less than or equal to m if we take the guess to be 0.5. So again, we just take the original margin of error formula, that part of the confidence interval formula, and for a particular value solve for. Suppose we want to determine what percentage of voters favor a particular candidate. We want to determine the sample size needed to estimate the population proportion within 0.03 with a 95% confidence level. So the critical value, z star equals 1.96. Since we want a margin of error of no more than 0.03, we need to solve the following equation. Where p star here is our best guess for the sample proportion. Keep in mind, we can always use 0.5 if we don't know. And that's what we'll do in this case. So the sample size we need is the z star, 1.96, over our margin of error, 0.03, squared, times 0.5 times 1 minus 0.5. Or in this case, we get 1067.1, and we round up to 1068 to ensure the margin of error is no more than 0.03 at this. Now, significant tests for a proportion. The z-statistic has approximately the standard normal distribution when the null hypothesis is true. P-values, as we had before, come from the standard normal distribution. So here's a summary of the details for a z-test for a proportion. We choose a simple random sample of size n from a large population that contains an unknown proportion of successes. To test the hypothesis, the null hypothesis, that the population parameter, the population proportion, equals some value, we calculate the z-statistic in this way. So it's the sample proportion minus the hypothesized proportion over the hypothesized proportion times 1 minus the hypothesized proportion divided by n, the square root of that. And then we have the usual one-sided and two-sided tests depending on the alternative hypothesis. Now, as a measure of the condition, we can only use this test when the expected numbers of successes and failures are both at least 10. So, for example, a potato chip producer has just received a truckload of potatoes from its main supplier. If the producer determines that more than 8% of the potatoes in the sample have blemishes, the truck will be sent away to get another load from the supplier. A supervisor selects a random sample of 500 potatoes from the truck. An inspection reveals that 47 of the potatoes have blemishes, and we want to carry out a significance test at the 0.1 significance level. And what should we conclude? So, state the hypotheses. At the 0.1 level of significance, the null hypothesis is that the population proportion of all blemished potatoes is 0.08. The alternate hypothesis is that the proportion is greater than 0.08. And in this case, again, P is the actual proportion of potatoes in the shipment with blemishes. So if the conditions are met, we can use a one-sample Z test for the population proportion. Is it random? Well, we're told that it is. Normal? So assuming that the null hypothesis P equals 0.08 is true, the expected number of blemishes and unblemished potatoes are 500 times 0.08, or 40, and 500 times 0.92, 460, respectively. So because both of these values are at least 10, we're safe in doing normal calculations. Notice the formula there, n times P0. So there we're saying if we have 500 from a sample, we can multiply by our estimate 0.08. So the sample proportion of blemished potatoes is P hat equals 47 over 500, or 0.094. And then we can calculate the test statistic. So Z equals the sample proportion minus the hypothesized proportion divided by the standard error. So in this case, that's 0.094 minus 0.08 over the square root of 0.08 times 0.92 over 500. And our Z-score is 1.15. So to find the p-value, we're looking for the area associated with a z-score of 1.15 or greater. And from the normal distribution table, we find that that the area to the left of the z equals 1.15 is 0.8749. So we want the other side of that. 1 minus that is 0.1251. So since our p-value, 0.1251, is greater than the chosen level of significance, 0.1, we fail to reject the null hypothesis. There is not sufficient evidence to conclude that the shipment contains more than 8% blemished potatoes. So the producer will use this truckload of potatoes to make potato chips. To review, we described and checked the conditions necessary for inference, construct and interpret large sample and accurate confidence intervals for a proportion, calculate the sample size necessary for a level C confidence interval, and conduct a significance test for a proportion.